Hello everyone, welcome to Stat 310 Lecture 22. This will be the final lecture on content for this course. And so we're finishing off on kind of the final key concept, which is simple linear regression. And it's going to be sections 14.1 and 14.2 of the textbook. So this was something we started in the previous lecture, lecture 21, and we're going to essentially just finish off that discussion today by essentially talking about the distributions and the confidence intervals and talking about doing hypothesis testing for the parameters associated with simple linear regression. So the previous lecture focused on just estimates, like point estimates for the parameters, and now we're going to focus on, and today we're going to focus on the distributional properties of these, and then we're going to finish with an example where we do some calculations in this context. So just to kind of put things back into the statistical framework as we've done typically in the course. So remember here that our data here is we have xi, which is like a feature or a covariate, and then our yi, which is the dependent variable, which depends on the xi, which is you can think of as the independent variable. And then the model that we have is the so-called linear model. And it's linear because we assume this kind of linear relationship between the covariate and the response, or the dependent and independent variable. And we kind of assume throughout that the noise here is normally distributed with mean zero and variance sigma squared. We don't have to assume that to get a regression line, but we are going to assume that, and that's going to be important when we start to talk about the distributions of these parameters. So the parameters of interest here are beta 0, beta 1, and sigma squared. So another way to think about this distribution is that y is normally distributed with mean beta 0 plus beta 1 xi and variance of sigma squared. And what we spent the majority of the previous lecture talking about was the estimators for these parameters. So remember that the least squares or maximum likelihood estimates gave that we had. So if we define the statistics, so if we define the statistics, we've got the mean of the x's, the mean of the y's. Then we have the variance of the x's, and the variance of the y's. And then we have the population, or the sample, correlation coefficient. As we saw in the previous lecture, this kind of allows us to define our estimates kind of in a nice, straightforward way. So we had that. So our estimators could all be expressed in terms of the statistics. So we have that beta hat 1, which is the slope, was just rho hat times sigma times sy over sx. Then our beta hat 0 was just y bar minus beta hat 1 x bar. And this just ensures that line goes through point, the line goes through the point x bar, y bar. Okay, and then we also had this estimate sigma hat squared, which is the residual sum of squares divided by n minus 2. This is like the degrees of freedom, where the residual sum of squares is equal to in some sense, it's called the residual sum of squares because if we subtract off the estimates of beta hat and beta 1 under this linear model, it's just kind of the sum of squares of whatever's left over, and that's our estimate, and we need to divide by n minus 2 because we have n minus 2 degrees of freedom. So this is like n minus 2 degrees of freedom. So today we focus on for the distributions of beta hat 0, beta hat 1, and sigma hat squared. And then we talk about analysis. So this is essentially, if we want to find confidence intervals, or if we want to do hypothesis tests. And once we have the distributions, we can do these things. Okay, so I guess one thing I just wanted to clean up first was that what we finished talking about in the previous lecture was that we have that beta hat 1 is one way to express it was like this. And one thing to always keep in mind here, and I mentioned this in the previous lecture, but I'll mention it again here, is that the y's here are treated as random variables while the x's are treated as fixed. So the x's are kind of fixed numbers, whereas the y is a random variable. And that's always important to think about when you're taking means and variances. And we have that this quantity for beta hat 0. And so one thing to note is that since beta hat 1 and beta hat 0 are linear combinations, or linear combination of the yi's, then we know that beta hat 1 and beta hat 0 are normally distributed. So this is already kind of a, this is already a very kind of useful thing. And so what that means is that we have that beta hat 1 is going to be normally distributed with a mean, and from the previous lecture we know that mean is beta 1 because we calculated that, and then we have the variance of beta hat 1, and then beta hat 2 is normally distributed, or beta hat 0, normally distributed with mean of beta 0, and then the variance of beta hat 0. Okay, so therefore we need to just work out, okay, so what's the variance of beta hat 0 and beta hat 1? And this is a calculation I'm not going to go through explicitly. It's quite, it's just very technical, and it's provided in the textbook. It's not a calculation you'll need to repeat for the exams. I mean, you could, if you wanted to, you could just use the formula. But I'd say it's still worth kind of just going through it in the textbook. But what you can kind of show is that the variance of beta hat 1 is equal to sigma squared over n times sx squared, and then the variance of beta hat 0 is equal to we've got the same thing, but then we have this extra term that's okay. So therefore we have that it's okay, and then the next thing that we need to worry about, and this is going to be pretty useful when, in the case particularly when sigma squared's unknown, is the distribution of sigma hat squared. Potentially some of you could already guess that we know that sigma hat squared is equal to RSS over n minus 2, where this residual sum of squares is okay, and it's fairly straightforward to show, or not fairly straightforward, but it can be shown that something that's reasonably intuitively true, which is that if you look at n minus 2 times sigma hat squared and then you divide by your sigma squared, that's going to have a chi-squared n minus 2 distribution. So whenever you're dealing with residual sum of squares under the normal distribution, you're kind of expecting it to be a chi-squared distribution if you appropriately normalize it. And you can certainly show that that's going to be a chi-squared with n minus 2 degrees of freedom. And again, the n minus 2 comes from the fact that you have n samples and then you lose one for each of the two parameters, beta 0 and beta 1. And so this result's also really useful because what that kind of means is that, if sigma squared is unknown, how do we deal with that typically? When we're dealing with a normal distribution, we can, use the t distribution because we know that sigma hat squared's got a chi-square distribution. So what that essentially means is that if you look at beta hat 1 minus beta 1 over, and then if we divide that by sigma hat over square root of n times sx, which is the square root of the variance. That's going to have a t-squared distribution with n minus 2 degrees of freedom because we know that sigma hat, in some sense, the numerator and the denominator are both going to contain sigma, and they're going to cancel out, and you're going to get a normal normal divided by the square root of a chi-squared. So, and then we also have that beta hat 0, and then so then if we look at beta hat 0, that's also going to have a t distribution once we kind of renormalize properly. And so what this also means is if we want to test there's two different hypotheses we could test here. One is that beta 1 is equal to 0, and the other one would be that beta 0 is equal to 0. So the intercept or the slope are 0. So we could just use a standard t-test. Because under H0, if we're looking at beta 1, we have that beta hat 1 is distributed as Tn minus 2, and beta hat 0 over square root of this is going to be distributed as Tn minus 2. So you can do whatever test you want, one-sided, two-sided, or anything else, using this result, and we will do that right at the end of today's lecture. So the final, so one of the other key pieces that I haven't really spoken about yet is actually how you calculate this sigma hat squared. So in many settings, you may not have access to the whole data set, have access to the data set, you know, xi, yi. So, and this includes kind of exam questions or homework questions you may get. You only have access to the summary statistics, which I mentioned earlier, which are x bar, y bar, sx squared, sy squared, and rho hat. So, and these are kind of the sample means, the sample variances, and the sample correlation. And so the question is then so we know how to calculate beta hat 0 and beta hat 1 from these summary statistics. How about if we want to do, if we want to go to the next step and want to if we want to find confidence intervals, or do hypothesis tests, if we want to find confidence intervals or do hypothesis tests, you certainly need to calculate, need to find sigma hat squared, and you also need this other quantity for beta hat 0. And so the question is, how do we calculate these from our summary statistics? Okay. So hopefully for 1 over n summation I equals 1 to xi squared, you can sort of hopefully see that that's just sx squared plus x bar squared. That's something that you can hopefully just kind of take a look at and see that that's true, and that comes from the fact that we have that sx squared is 1 over n, and that just equals 2 and then minus x bar squared. Okay, so that's something that you can check yourself, but this kind of gives you a way to calculate that that quantity. And the reason I mention that is because that's going to be for beta hat 0. That quantity appears in the variance for beta hat 0. And then the kind of the more challenging and interesting question is, calculating sigma hat squared in terms of x bar, y bar, sx squared, sy squared, and rho hat. So we know that sigma hat squared is equal to residual sum of squares over n minus 2, and so that's 1 over n minus 2 Okay, so we know that this is what that looks like, and so let's just deal specifically with the residual sum of squares, and then we'll factor in the n minus 2 later. So if we look at the residual sum of squares, like, you know, how can we get that in terms of these like just these sort of quantities that we already know, these 5 summary statistics? The key step is you can kind of add and subtract y bar and x bar. So we're just going to take that, and then we're going to then subtract xi minus x bar. And then you can kind of add and subtract them both back in. And so you're going to get, and then then you're going to get minus beta hat 0 plus y bar, and then minus beta hat 1 x bar. And then this whole thing's squared. So all I've done is kind of added, subtract this thing. But what's kind of important to note there is that we have this term y bar minus beta hat 1 x bar minus beta hat 0, and we know that that thing is equal to 0, right? Because that was the first kind of key equation, you know, since we know that beta hat 0 equals y bar minus beta hat 1 x bar. Okay, and so what this means is that whole residual sum of squares starts to look a lot nicer, and in terms of you know, quantities that we already know, which is, you know, so that should be beta hat 1. Okay, and so we now can write this in this way. And we can now split this up as, we can sort of break these terms up, and we get okay, and then we also have the cross term, so we're going to get minus 2 beta hat 1 . Okay, and so what we can see is that this relates to some of these quantities that we already have. This is just, the first term here is just n times sy squared. The second term here is just plus beta hat 1 squared, and then it's going to be times rho hat. It's just going to be rho hat times, sorry, that is incorrect. This thing should just be xi minus x bar squared. So this is just going to be beta hat 1 times n times sx squared. And then that last term is going to be 2 times beta hat 1, and then times rho hat, and then we have to multiply by the two variances because we divide by them. So this is what we end up in. This is kind of nice because now we have this this quantity in terms of just what we already know. And also note that beta hat 1 here is just rho hat sy over sx. So therefore we have that the residual sum of squares just n times sy squared, and then plus rho hat squared, or let's just take out the n here. So I'm just going to take out the n because it's common here across. So that there should also be an n in here that I didn't include. So that this is just sy squared, and then plus rho hat squared sy squared. And see, and then this is going to be minus 2 times rho hat squared. And then we're going to get the sy and the sx will cancel out again. So you get sy squared. And so this whole thing is just going to be n times sy squared times 1 minus rho hat squared. So it's pretty cool that that's what we get as the residual sum of squares is just n times sy squared over 1 minus rho hat squared. And so therefore what that means is that sigma hat squared is equal to n times sy squared 1 minus rho hat squared divided by n minus 2. Okay, and one thing you might sort of wonder is, why do we divide by n minus 2? Because you would think, if we divided by n, then, this expression looks a little bit nicer. The reason we do that is this is not something we're going to show, but it's very related to a couple of the other things we've seen in the course. By dividing by n minus 2, we have that expectation of sigma hat squared is equal to sigma squared. So if we didn't divide by the n minus 2 here, we wouldn't actually get that expression, but because we divide, that's why we get this unbiasedness. Okay, and so so just to summarize that, in summary, we've kind of done all the calculations we now need to sort of do anything we want to do with simple linear regression. So if we define if we define this if we define the summary statistics so these are the population variances, and then of course the correlation coefficient. Then we have that beta hat 0 I will start with beta hat 1. Beta hat 0 is just and I'll just write it out explicitly. This is what that our beta hat 0 is, and then we also have that sigma hat squared is equal to n divided by n minus 2 of rho hat 1 minus s. Sorry, that is incorrect. Sorry. We have that sigma hat squared is n over n minus 2 times sy squared, or the variance of y times 1 minus rho hat squared, and And then this last thing here, which is, you'll see why we have that. That's just equal to sx squared plus x bar squared. And so why is this relevant? So what that means is that that all of these quantities now we can kind of get everything now in terms of our t distributions here. So okay. So now we're kind of now in a position to answer any question that we want to. So we're going to spend kind of the next kind of bit just going through that to sort of finish with. So let's do an example. So we have so we've got a data set xi, yi I equals 1 to 100. So here we've got n equals 100, where I'm not telling you what the explicitly each data point is, but we know that x bar is 1, y bar is 3, rho hat, the sample correlation coefficient is a half, sx squared is 1, and sy squared is 4. So for part 1, we want to find estimates for beta hat 0, beta hat 1, and sigma hat squared. Part 2, we want to find 95% confidence intervals for beta hat 0 and beta hat 1. And for part 3, we're going to perform a test for hypotheses H0, which is beta 0 is 0, or the second one is and we're going to do that against two-sided alternative with alpha, the significance level equals 0.05, and hopefully you're already potentially thinking in your mind that 2 and 3 are going to be related because of the duality between hypothesis testing and confidence intervals, and we'll talk about that more shortly. So now we'll go through this. So for 1, we have that beta hat 1 is rho hat sy over sx, and so that's just equal to we have that rho hat's a half, sy here is equal to 2 because sy squared is 4 and sx is 1, so it's just equal to half and 1, so that's just 1. Beta hat 0 is equal to y bar minus beta hat 1 x bar. Y bar here is 3. Beta hat 1 is 1 and x bar is 1, and so that just is 2. So what that essentially means then is our regression line just looks like, so let me not use that index that is confusing. So the regression line here, if we look at x versus y, so we have the intercept here is 2 and the slope is 1. So the regression line essentially just looks like that. So this is 2, and then it obviously goes through the point 2 here, and it goes to the point -2 here. So that's what the regression line would look like here. And then we want to also find an estimate for sigma hat squared. So that's going to be n divided by n minus 2 sy squared 1 minus rho hat squared. And so that's going to be 100 divided by 98, which is it's pretty close to 1. And then sy squared is 4, and then we have 1 minus 1/4. So this is going to be about 3.0, and that's what our sigma hat squared is. The next thing we want to do is to find 95% confidence intervals for beta 0 and beta 1. So we know that beta had 1 over beta had 1 minus beta 1, and then we have divided by sigma hat over square root of n times sx is t n minus 2. So what that means is that 95% confidence interval for beta 1 is just going to be beta 1 as in beta hat 1 as our center point, and then plus or minus, and then we're going to have t n minus 2, and then we're going to have like 0.025 as that cutoff point, and we're going to multiply that by sigma hat over square root of n times sx. So the center point here is 1, and then we're going to add the this quantity. You can just look up on a t table. I believe it's about 1.94, but you can check that. In some sense, like when so this should be a 98 here. So t98 0.025. So I'll just make that explicit here. This is going to be t98. When n is that big, like the t and the normal are very, very close. So as n gets bigger and bigger, t starts to look more and more like a normal distribution. So the normal table will probably give you pretty accurate results in this case. And then we have 3.0 divided by 10, which is the square root of 100, and then times sx, which is 1. And so you're going to get 1 plus or minus about 0.6 as our 95% confidence interval. So you're just going to get a confidence interval of about 0.4 and then 1.6 as our confidence interval. Okay, and then for beta 0, we know that beta hat 0 minus beta 0, and then you divide by sigma hat over square root of n sx, but then you have to add this sx squared plus x bar squared term. This is going to be t, I'll just put 98. And so the 95% confidence interval is going to be it's going to be beta hat 0 and then plus or minus, and then we're going to have t 98, and then 0.025 again, because it's a two-sided test, and then we're going to have sigma hat divided by square root of n sx as we had before, but now we're going to have this extra term of sx squared plus x bar squared. Okay, and so now if we just if we plug in the numbers, beta hat 0 is 2, so beta 0 is in 2, and then plus or minus, and we're going to get again 1.94, and then we're again going to get times about 0.3, and then sx squared plus x bar. So this should be a square root, I'm sorry. That's a mistake. So this should be times the square root of sx squared is 1, and so this is just going to be 1 plus 1. And so this is going to be 2 plus or minus 1.94 times 0.3, and then times about 1.4. And so you're going to get 2 plus or minus. And if I do this calculation right, it's going to be about 0.85 roughly. So or 0.8. I think it's 0.84 if we round it, and so we're just going to round it down to 0.8. And so so our 95% confidence interval is going to be 1.2 to 2.8, and so that's so that gives you the confidence intervals. And then the final thing is if we want to test, we've got these two hypotheses, so I'll call them a bit differently, 1 and 2 like this. So beta 1 equals 0, and then beta 0 equals 0. So here you're going to reject H naught, since the 95% confidence interval does not contain 0 for both beta 0 and beta 1. Okay, so because the alpha was equal to, here we've got alpha equals 0.05, so using the duality between hypothesis testing and confidence intervals, we can say that you're going to clearly reject the null hypothesis. Okay, and so that just kind of gives you a flavor of how to answer a question involving regression. And importantly, one thing to remember there is that we didn't actually ever look at the raw data. We just had access to those 5 summary statistics, but that was enough for us to be able to do all the calculations that we needed. Okay, so the summary of our simple linear regression in our framework. So this is going to be in our framework. So for one, we have that our data is xi, yi, I equals 1 to n. Our second key point is that our model here is so with the parameters of interest here are beta 0, beta 1, and sigma squared. And then the third thing here is the estimators, which is largely covered in the previous lecture, where we have that I'm not going to write out the definitions again because I've already done it about 3 times in lecture. So if we have the summary statistics, x bar, y bar, sx squared, sy squared, and rho hat, we have that beta hat 0 is equal to y bar minus x bar times rho hat sy over sx. Beta hat 1 is equal to like rho hat times sy over sx. And then we have that sigma hat squared is equal to n minus 2 over n. And then 1 minus rho hat squared times sy squared. And then if we look at the distributions, if we look at the distributions of our statistics, we have that beta hat 0 is normal with mean of beta 0. And then our variance that we calculated was sigma squared over n sx squared our beta hat 1 was normally distributed with beta mean of beta 1 and then the variance of sx squared, and then the sigma hat squared had this chi-squared distribution. So n minus 2 times sorry, I made a mistake here. This should be the other way around. It should be n divided by n minus 2. That's what I got wrong. So this should be n divided by n minus 2. So we have n minus 2 times sigma hat squared over sigma squared is chi squared n minus 2. And so what that also leads to then is that beta hat 0 minus beta 0 So then if we wanted to do inference in the case where our sigma squareds are known, which is usually the case, this is how we can use the t distribution. Okay, so this is what we have for our for part 4, and then for the 5th part, which is the analysis. If we want 1 minus alpha times 100% confidence intervals, and we're talking about two-sided here. Two-sided, then we can kind of say, so for beta 0, we have that's just beta hat 0 plus or minus, since it's going to be t n minus 2, and then we're going to have alpha divided by 2 is the parameter, and then and then for beta 1, we're going to have okay, so then this is what we have for the confidence intervals for beta hat 1, and similarly can perform any hypothesis test using this distribution. Okay, so that kind of covers everything that from chapter 14 that you'll need, and essentially that's everything for the course. And so just kind of in summary, what have we done since midterm 2? Because we have another few minutes, I'll just kind of go through this so that you can, after you're done with the last homework, which will cover simple linear regression in terms of preparation for the final. Since midterm 2, what we've covered is so chapters 8 and 9 were the two chapters we spent the most time on because they laid the foundation for estimation and hypothesis testing. And so since midterm 2, there's really been a focus on looking at different examples that go beyond just a simple kind of single sample. So we're looking at examples beyond simple single independent samples. So we covered, paired samples. So we covered, the kind of the next sort of case, which was two samples, which was chapter 11. Then we covered ANOVA, which was chapter 12. And so that's the example where, rather than having like two sets of samples, you might have like I sets of samples where you have I different groups, and we looked at both one-way and two-way ANOVA. And then we looked at linear regression. Which was chapter 14. And so again, this was another case where our data is now not just drawn IID from a sample, but we have this covariate XI and then this response YI. And so in some sense, like all of the principles were really developed in chapters 8 and 9, where we talked about estimation and hypothesis testing for when you have one independent samples. And then what we did since midterm 2, which focused on chapters 11, 12, and 14, really looked at the scenario where you kind of look at beyond one sample, what kind of inference can you draw? But a lot of the foundations were already, a lot of the ideas were really very similar to what we'd already seen in chapters 8 and 9. Okay, thanks very much, and good luck in the study for the final. We'll be in touch by email, by announcements and emails, and on the website. Okay, thank you.